So, hello, my dear students. Once again, welcome back to our online education platform for the integrated classes, the VAVA classes. So, students, now we'll discuss one example. Let A equal to 1, 2, 3 be a set, and relation R is defined on the set A. R equal to 3, 1, 1, 2, 3, 3, 1, 3, 2, 1. Okay. Now, you can see that relation is symmetric. Since 3 1 belongs to R, that implies 1 3 belongs to R. 1 2 belongs to R, 2 1 belongs to R, 1 3 belongs to R, 3 1 belongs to R, 2 1 belongs to R, 1 2 belongs to R. So the relation is symmetric. For all AP belongs to R, that implies BA belongs to R. Okay, so the relation is symmetric. Okay, so for every AB belongs to, for all AB belongs to R, that implies BA belongs to R. So the relation is symmetric. But the relation R1 defined on A as R1 equal to 3 1 1 2 3 3 1 3 2 2. Here 1 2 does not belong, 1 2 belongs to R1, but its reverse 2 1 does not belong to R1. So R1 is not symmetric. Relation R on A is said to be non-symmetric if there exists at least one AB belongs to R, but BA does not belong to R. So then it is called non-symmetric relation. Transitive relation. Let A be a non-empty set. Then a relation R on A is said to be transitive if AB belongs to R and BC belongs to R. That implies AC belongs to R, where ABC belongs to A. That is, A is related to E with B, B related with C. That implies A related with C, where ABC belongs to A. Okay, so that is called transitive relation. In a real life example, we have discussed if A is friend of B, B is friend of C, or you can say that if A is greater than B, B is greater than C, then A is greater than, sorry, if A is less than B, B is less than C, then A is less than C. That is less than relation is transitive relation. Okay, you can give similar example in real life, similar real life example or mathematical statement you can give. For example, relation greater than equal to on the set of real number is a transitive relation. Less than equal to also transitive relation. Relation of divisibility also on the set of natural number is also transitive relation. Okay. If A divides B, C divides equal. If A divides B and B divides C, that implies A divides C. 2 divide 4, 4 divide 8, that implies 2 divide 8 because of transitivity. 2 divide 4, 4 divide 8, that implies 2 divide 8. So transitivity. This is transitive relation. Okay. Let A equal to 1, 2, 3 be a set and relation R is defined on A as R equal to 1, 1, 3, 1, 1, 2, 3, 3, 1, 3, 2, 1, 2, 2. Since 3, 1 belongs to R, 1, 3 belongs to R, and 3, 3 belongs to R. 1, 2 belongs to R, 2, 1 belongs to R, 1, 1 belongs to R. So 2, 1 belongs to R, 1, 2 belongs to R, 2, 2 belongs to R. So the relation is transitive because for all AB belongs to R, BC belongs to R, that implies AC belongs to R. For every AB belongs to R, BC belongs to R, that implies AC belongs to R. So the relation is transitive. Okay. But the relation R1 defined on A as R1 equal to 1, 1, 3, 1, 1, 2, 3, 3, 1, 3, 2, 1. Here 2, 1, 1, 2 belongs to R1, but 2, 2 does not belong to R1. Hence R1 is not transitive. Here R1 is not transitive because for 2, 1, 1, 2 belongs to R1, 2, 2 does not belong to R1. So for at least one AB belongs to R, BC belongs to R. For at least one AB, BC belongs to R, but SC does not belong to R. Then we say that the relation is non-transitive. Okay. Now we have some assignment question you have to do yourself. Let A equal to 0, 1, 2, 3 be a set and R is the relation. define on A as R equal to 0, 0, 0, 1, 0, 3, 1, 0, 1, 1, 2, 2, 3, 0, 3, 3. We have to verify whether R is reflexive, R is symmetric, or R is transitive or not. Okay, so try to do yourself. Similarly, the students, you can solve here as well. Here, R contains 0, 0, 0, 1, 0, 3, 1, 0, 1, 1, 2, 2, 3, 3, 3, 0, 3, 3. There is no S, so the relation is reflexive. Clearly, it contains 0, 0, 1, 1, 2, 2, 3, 3, so the relation is reflexive. Now, here, it contains 0, 1, 1, 0, 0, 3, 3, 0. So, for every AB belongs to R, BA belongs to R, so it is symmetric. Now, transitive 0, 3, 3, 0, it is 0, 0 is there, 1, 0, 0, 1, 1, 1 is there, 0, 3, 3, 0, 0 is there. So, for all FB belongs to R and BA belongs to R, okay, or for AB belongs to R, BC belongs to R, we have AC belongs to R. So, the relation is transitive, okay, so it is transitive. Now, question number 2. A equal to 1, 2, 3, 4 be a set and R is a relation defined on A, R equal to order pair AB such that A minus B mod is even. Okay. Now, what are the element in R? Since A equal to 1, 2, 3, 4, 5. Okay. So, A into A contain 25 elements. And what are these 25 elements? So, A into A equal to order pair AB such that AB belongs to A. Okay. So it contains 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5. Okay. These are the element in A into A. Now R is a subset of A into A. R is a relation on A. Okay. R is defined that order pair AB such that B minus A mod is even. Okay. Now, for A minus A, for every A belongs to the set A. For every A belongs to the set A minus A mod equal to 0 and 0 is always even. So, A minus A is 0 is even. So, that implies A belongs to R. For all A belongs to A. So, R is reflexive. R is reflexive. Now, you can see here, if B minus A mod is even, that implies A minus B mod is also even. Okay, if B minus A mod is even, that implies A minus B mod is also even. That implies R is symmetric. If B minus A mod is even, then A minus B mod is even. So R is symmetric. Clearly, R is symmetric. Okay. So B minus A mod is even, that implies A minus B mod is even. So R is symmetric. Clear. Okay. Now what about transitive? If B minus A mod is even, so both B and A should be even, or both B and A should be odd. Okay. And now consider what are the element, what are the possible element in this set? A equal to 1, 2, 3, 4, 5. R equal to order pair AB such that B minus A mod is even. So R must contain element like 1, 1, 1, 3, 1, 5, 2, 2, 2, 4, 3, 3, 3, 5. 4 4, 4 2, 5 1, 5 3, 5 5. Okay, because if you subtract in this case, a minus b is even. Now see clearly, for 1 3 and 3 5 we have 1 5. For 2 2 2 4 2 4 is there. For 5 1 1 5 5 5 is there. Okay, so for all AB belongs to R, BC belongs to R, we have AC belongs to R, so the relation is transitive. Okay, now question number 3. Let R be relation defined on set of natural number n as R equal to order pair xy such that xy belongs to natural number 2x plus y equal to 41. Okay, verify whether the relation is reflexive, symmetric, or transitive. 2x plus y equal to 41. Now for 2x plus x, suppose x is y. So for 2x plus x equal to 41, 3x equal to 41, x equal to 41 by 3, it is not a natural number. X equal to 41 by 3, it is not a natural number. So since it is not a natural number, 2x plus x equal to 41, 3x equal to 41, x equal to 41 by 3, it is not a natural number. Since it is not a natural number, so we can say that it is not reflexive. Now, suppose x is 2x plus y is 41. Suppose x is 20, y is 1. Then 2 into x plus y is 2 into 20 plus 1. 40 plus 1 is 41. Now, x plus x. So, xy belongs to R. Now, for yx2 belongs to R, we have to write x plus 2y or 2y plus x. What is x plus 2y? 20 plus 2 into 1. That is 22. Is not equal to 41. So, since it is not equal to 41, so it is not symmetric. Okay, it is not symmetric. Again, it is also not transitive. You can verify yourself. Okay, now we'll discuss some subtopic equivalence relation. Outline the definition of equivalence relation and some of the examples. Assignment problem will be solved here. Equivalence relation. A relation which is reflexive, symmetric, and transitive is called equivalence relation. Okay, a relation which is reflexive, symmetric, and transitive is called equivalence relation. Let R be a relation on set of rational number defined by order pair AB such that A minus B belongs to Z, where AB belongs to Q, so that R is an equivalence relation. Very, very interesting question. Here R equal to solution, R equal to order pair AP, so that A minus B belongs to Z, where AP belongs to rational number. To show it is an equivalence relation, we have to show it as reflexive, symmetric, and transitive. In order to show it is equivalence relation, we have to show it is reflexive, symmetric, and transitive. So first relationship, reflexive. As we know that 0 is an integer and x minus x equal to 0 for all x, whether it is belongs to q or not. Okay, also for all x belongs to q, x minus x is 0. So 0 is a integer. Okay, so for all a belongs to q, a minus a equal to 0 belongs to z. So hence a belongs to the relation for all a belongs to q. So it is reflexive. So R is a reflexive relation. Now the example. Also here the same example, we'll verify the symmetry. Let AB belongs to R, that implies A minus B belongs to Z. That is A minus B is an integer. If A minus B is an integer, then minus A minus B is also is an integer. That implies B minus A is an integer. So B minus A belongs to Z. Okay. So for AB belongs to R, implies BA belongs to R. AB here is arbitrary. You can choose any AB. Then for that, then BA also belongs to R. Hence R is symmetric. Now transitivity. Let AB belongs to R and BC belongs to R. That implies A minus B and B minus C are integers. So A minus B plus B minus C is also integer. So A minus C is an B minus plus B cancel. So A minus C is also an integer. Okay. So it is transitivity. So reflexive symmetry and transitivity we have proved. So here, so for AB and BC belongs to R, we have AC belongs to R. So R is transitive relation. So R is reflexive, symmetric, and transitive. So it is an equivalence relation. Now next question. So that the relation R in the set n cross n defined by order pair AP R CT, AP related to CT, is equivalent to a square plus d square equal to b square plus c square for all ABCD belongs to n is an equivalence relation. Here, the set is itself a order pair n cross n, and we are forming the relation R. Suppose n cross n equal to suppose the any set n star. So we are forming the relation R in the subset of n star cross n star. Since R is defined as AP related to CT is equivalent to a square plus d square equal to b square plus c square for all a b c t belong to n. Now reflexivity. Since we know that a square plus b square equal to b square plus a square for all a b belongs to n. So a b related to a b for all a b belongs to n into n. That implies R is reflexive clearly. Again, uh, for a square plus d square equal to b square plus c square, we have b square plus c square equal to a square plus d square. Okay. Now, since f related to ct, we have a square plus d square equal to b square plus c square. So we can write b square plus c square equal to a square plus d square. That implies c square plus b square equal to d square plus c square. That is ct belongs to ct related to fb. So FB related to CD, we have CD related to FB. So R is symmetric. Okay. So FB related to CD, that implies CD related to FB. So R is symmetric. Transitivity. Let FB related with CD, that implies A square plus D square equal to B square plus C square. This is equation 1. Again, CD belongs CD related with EF. So C square plus F square equal to D square plus C square. This is equation 2. Add I and double I. Add I and double I. So a square plus d square plus c square plus f square equal to b square plus c square plus d square plus e square. That implies a square plus f square equal to b square plus e square. That implies fb related with ef. Hence R is transitive. Hence R is transitive. Now we have proved here R is reflexive, R is symmetric, and R is transitive. So R is an equivalence relation, students. Now we'll solve another assignment here. Given a non-empty set X, consider P of X, which is the set of all subset of X. Define a relation in Px as follows. For subset AB in Px, A related to B if yes, A related with B if A is subset of B. Okay, this is the relation. If the relation is subset in case of power set of X, so clearly it is a relation and it also a equivalence relation. We can prove. So that the relation R in the set n into n defined by AP related with CT is equivalent to AD whole into B plus C equal to BC whole into A plus D. For all ABCD belongs to n is an equivalence relation. Okay. We can also verify that it is an equivalence relation. Okay, AP related to CT is same as AT whole into B plus C. Okay, AD whole into B plus C equal to BC whole into A plus D. We have to show that it is an equivalence relation. Okay, so now I'll show question number 2. Here, FB related to city is equivalent to a d whole into b plus c is equal to bc whole into a plus d. Okay, a d whole into b plus c equal to bc whole into a plus d. Now we have to show that it is an equivalence relation. First, we have to show it is reflexive. Now, uh, if FB related with FB, okay, when FB related with FB, you see A B into B plus A equal to B A whole into A plus B. Since AB into B plus A equal to BA into A plus B, because AB into B plus A, here BA is same as AB into A plus B. Again, FB into B plus A is FB into A plus B equal to FB into A plus B. Okay. So FB into A plus B is same as FB into A plus B. That implies this FB into B plus A equal to BA into A plus B. That implies FB related to FB. So it is reflexive. Now symmetric. If FB related to CT, that implies AD into B plus C equal to BC into A plus D. We need to show CT is related with FB. That implies we need to show AD, that is BC whole into B plus C whole into A plus D equal to now this is AD, BC is there, again BC, so it should be AD whole into A plus D, so B plus C. Okay, so this is same, AD into B plus C equal to BC into A plus, this is obvious. So that implies CT related with AB. So AB related with CT, that implies CT related with AB. So it is symmetric. Okay. Now transitive. You can verify here. Now CD related with EF is equivalent to CD related with EF. So we have AD whole into B plus C. We have CF whole into D plus E is equal to DE whole into C plus F. Okay. We need to prove FB is related to EF. We need to prove this. That is, it is equivalent to proof uh, CF whole into D plus E. CF whole into D plus E. So it is AF whole into B plus E is equal to DE is equal to BE whole into A plus F. We need to show this. Okay. AF into B plus E equal to BE whole into A plus F. By simplification from these two relations, if you simplify, we can prove this. Okay. So you try to solve yourself. Otherwise, we will solve this in the after classes. Just multiply and simplify. You see, you will reach it here. So it is a equivalence relation. Now, question number 3. What is given? Let n be a positive integer. Prove that the relation R on the set Z of all the integer defined by order pair AB belongs to R is equivalent to x minus y is divisible by n. Okay, x minus y is divisible by n is an equivalence relation. Clearly, x minus x is 0 divisible by n, so it is reflexive. If x minus y is divisible by n, that implies y minus x is also divisible by n. If so, it is symmetric. So x minus y divisible by n, y minus z divisible by n, so it's addition. X minus z divisible by n, that is xy belongs to R, yz belongs to R, so xz belongs to R. Okay. So x minus x is 0 divided by n. So xx belongs to R. So it is reflexive. X minus y divided by n. So y minus x also divided by n. So it is symmetric. So xy belongs to R. That implies yx belongs to R. Now x minus y divided by n. Y minus z divided by n. X minus z divided by n. So it is symmetric. Okay. Because xy belongs to R, yz belongs to R. That implies xz belongs to R. So it is symmetric, sorry, transitive. So reflexive, symmetric, transitive. So it is a equivalence relation. Okay. So you can write it detail in your notebook. Now we'll solve some important question. Let A be the set of all human beings in a town at a particular time. Determine whether the following relation is reflexive, symmetric, and transitive. Okay. Now R equal to order pair xy such that x and y are work at same place. X related with x because x and x work at same place, so it is reflexive. If x and y work at same place, that implies y and x also work at same place, so it is symmetric. Now x and y work at same place, y z work at same place, so x z also work at same place. X and y work at same place, y and z work at same place, so x and z also work at same place, so it is transitive. Okay. So first relation is reflexive, symmetric, and transitive. Similarly, the second one you can see R equal to order pair xy so that x and y live in the same locality. X live in the same locality. If xy live in the same locality, then yx also belong to same locality. So it is trivially symmetric. It is reflexive. Now, what is xy live in same locality? YZ live in same locality, so XZ also belongs to in same locality. Okay, so it is transitive. So it is reflexive, symmetric, transitive. So I have done I and double I. This is your work to solve triple I and IB. You try to solve yourself. Okay. Otherwise, we will discuss that in the data classes. Now solution. Given R equal to order pair xy so that x and y work at same place. Yes. So we have already discussed there. So you can follow solution here as well. Okay. So third one you can see here. We have solved I and double I. Now third bit you can see. Given R equal to order pair xy so that x is y of y. Now we have to check whether the relation R is reflexive, symmetric, and transitive. First, let us check whether the relation is reflexive or not. Let x be an element of R. Then x is y of x. It cannot be possible. It cannot be true. So xx does not belong to R. So R is not a reflexive relation. Symmetric relation. Let xy belong to R. That is x is y of y. X is female, y is male. So y cannot be wife of x and y is husband of x. This is not possible. So yx does not belong to R. So R is not a symmetric relation. Now transitive. Let xy belongs to R, but yz does not belong to R. Since x is wife of y, but y cannot be the wife of z. Y is husband of x. So x is not the wife of z. That is xz belongs to R. So R is a transitive relation. So you can write that if xy belongs to R, yz does not belong to R. Okay. So here x is not the wife of z, so xz does not belong to R. So R is a transitive relation. What is the meaning of transitive relation? AB belongs to R, BC belongs to R, SC belongs to R. Sometimes AB belongs to R, but BC does not belong to R. That implies SC does not belong to R. So XY belongs to R, but YZ does not belong to R. But XZ also does not belong to R. So it is a transitive relation. Okay. Now question number 4. Given R equal to order pair XY so that X is father of Y. Now we have to check whether the relation is reflexive, symmetric, or transitive. Reflexivity. Let X be an arbiter element of R. Then X is father of X. cannot be true since no one can be father of himself. So R is not a reflexive relation. No one cannot be father of itself, so it is not a reflexive relation. Symmetry, let xy belongs to R. That implies x is father of y. So y is son or daughter of x. So y x does not belong to R. Okay, because this relation does not satisfy. So R is not a symmetric relation. Now transitivity. Let xy belongs to R and yz belongs to R. Then x is father of y and y is father of z. But x is grandfather of z, so the relation is completely changed. So xz is not equivalence relation. So xz does not belong to R. So R is not a transitive relation, friends.